our unit exam review will post tomorrow in Google Classroom, so you can start having a look over it over the weekend if you want to. We will cover the last 2 topics by Tuesday. Okay, we should have everything done by Tuesday of next week, and we'll do a unit exam review on like a formal one on Wednesday. It's a short unit, so I'm not too worried about that being the day before. Okay, hopefully you've done some review prior to that. Okay, so the thing with this unit, guys, is the unit exam for this unit is worth the same amount as the other 3. But this unit has 25% as much material as the other 3 units. So is it a pretty good opportunity to do well and raise your exam mark?
Yes.
Absolutely. Take it as such. Okay? There's really not a lot of material in this unit for you to know. Okay? That means that stuff is probably going to be tested multiple times in different ways on the unit exam. So it would be important to know it well. Right? If you spend the same amount of time studying for this test as you did for the others, especially physics, which you guys did really well on, you should do quite well because, well, mathematically speaking, you should know the material like almost 4 times as well. Okay, so make sure you make good use of that because obviously it's your last unit exam, and unit exams are a big portion of your mark. They just got bigger because I had to redistribute your marks because I had to change the weightings of everything to allot only 10% for your final instead of 20. So that all got evenly distributed between quizzes, coursework, and unit exams. So if you did notice that your mark changed a little bit last week, that's why. Okay. So yeah, it's a good opportunity to raise that portion of your mark before the final. All right, today we are going to be going over heat capacity and more specifically, specific heat capacity. And we're going to be doing a little bit of problem solving to do with that because it's part of basically the only problem solving that we have in this unit. So it's basically this and one other topic where there's any math, and everything else is the stuff we've been talking about up until now. So definitions here. Okay, heat capacity and specific heat capacity are very similar. All right, heat capacity is the amount of heat required to raise the temperature of an object by 1 degree Celsius. Okay, that's an object's heat capacity. Are objects generally made out of more than one material? Yes. Okay, and so that's why it isn't specific like the second one. Right? Specific heat capacity is a physical property of every material. Okay, so just like back in chemistry where we did the physical properties lab where we identified the unknown compounds, and the physical properties we were looking at were things like solubility, state of matter, okay, odor, color, all of those. Specific heat capacity is also a characteristic physical property unique to each substance. Right? So the specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so if we're saying this thing's specific heat capacity, we're saying here's how many joules of energy, thermal energy, would have to be applied to this object in order to, or to this substance, sorry, in order to make its temperature go up by 1 degree Celsius. Okay, so the units for specific heat capacity are joules per gram degree Celsius, because it's the amount of heat needed to change the temperature of 1 gram by 1 degree Celsius. Okay, so that's the units, joules per gram degree Celsius. All right, now there's a formula that we have that can be used to find the energy needed to heat up something. Okay, and that formula is E equals m times c times delta T. What does delta mean again? Nope. Change, right? So anytime we see delta, it means final minus initial. Okay, so When you're doing your delta T, this is sometimes a separate calculation, right? If a question gives you like, oh, here was the initial temperature and it's heated to this temperature, you have to do the subtraction operation first and then plug in that change number into that formula. Okay, so E equals M times C delta T, where E is the energy in joules. Okay, so E is the energy in joules, right? M is the mass in kilograms, or sorry, in grams. Sorry, in grams in this one, because this is chemistry. And delta T is the change in temperature. C is the specific heat capacity. Right, so little c here is the specific heat capacity. Each substance has a different heat capacity, specific heat capacity. Okay? Now, this is something that is important in terms of energy transfers, albedo, okay, all of that kind of stuff, when we're talking about global weather and climate and things like that. Thinking back to the other day, Vancouver and Calgary are about the same latitude, but Vancouver is considerably more mild in temperature and precipitation than Calgary. Why? That's the big one, is that Vancouver is close to the ocean. Okay, remember that your proximity to an ocean is a major factor affecting climate. The reason for that is the specific heat capacity of water. Water requires a huge amount of energy in order to change its temperature. Okay, for 1 gram of water, okay, 1 gram of water, which is 1 milliliter, will require 4.2 joules of energy to change its temperature by 1 degree Celsius. Okay, now I know, like you're looking at that and going, 4.2 joules doesn't seem like very much to go there. That's not a very big number. Okay, but we're talking about a very small amount of water. Okay? That is a very big number. Okay? To give you some comparison here, these are some specific heat capacities of other substances. Okay, so water is 4.2 joules per gram degree Celsius, right down here. Okay? Of all of these materials, it is the highest number. Okay? There's only a couple of things that are higher. Hydrogen being one of them. Okay? Hydrogen has like the highest specific heat capacity of anything else. Okay? And then helium is the second highest. Water next. Okay? So water requires a great deal of energy for its temperature to go up or down. Okay? It has to lose a lot of energy for its temperature to go down. That's why Vancouver's climate is so mild, why it rarely gets below 0 there. Okay? Because if the air temperature starts to get cold, the second law of thermodynamics says heat's going to go from the water, which is warm, into the air, which is cold, and they're going to achieve a state of equilibrium. Okay? Water can lose tons of heat, especially to something like air, which has a much lower specific heat capacity. Okay, if we're talking about equal masses of air and water, okay, the amount of temperature change that would happen with water and air exchanging energy would be that for every 4 degrees Celsius the air temperature changes, the water's temperature would only change by about 1 degree, actually a little less than 1 degree Celsius. Right? So it can cause very big changes and very big regulation to the climate and temperature of that area. Does that sort of make sense? Okay, that's the explanation as to why being close to the ocean can make your climate a bit more mild. Okay, so back to this here. So is this formula here, is it going to be relatively easy to use? E equals mass times specific heat times change in temperature. Everything is times. Is manipulating it going to be very easy? If I want to solve for something other than energy, what do? Divide everything else over to the other side. Super, super easy. You guys have used far more difficult formulas than that back in the last unit. Okay, so this one should not be algebraically challenging, okay, by any stretch of the imagination. Okay, let's have a look at a few examples of this. Every time I give you a new formula, I always go through a bunch of examples of that formula. So let's have a look at that. Okay, have you guys copy this one down here. How much heat, thermal energy, is needed to raise the temperature of 150 grams of water, okay, from 5 degrees to 85 degrees Celsius? Okay, give you a minute to get that written down here. So as always with any problem solving, the first thing we want to do is write down our givens. We are looking for how much thermal energy, okay, is needed, okay, to raise the temperature of 150 grams, that's our mass, of water. Okay, so they gave us the specific heat capacity, and sometimes they won't actually give you the number. They'll just tell you the substance, and then you'll have to refer back to your chart. This chart that I showed you a minute ago, this is like the first page in your Unit 4 worksheet package. Okay? On an exam, there's some specific heat capacities actually on your formula sheet, or I would actually give it to you on the cover of the exam or in the question of the exam. So you're never going to have to know what they are, okay, off the top of your head. And then we're going from 5 degrees to 85 degrees, so our temperature change is 80 degrees Celsius. All right, everybody with me so far? So, do we have to manipulate this formula at all? Already set up to solve for E, so we don't have to do anything except plug in our numbers. 150 grams times 4.2 joules per gram degree Celsius times 80 degrees Celsius. Sorry, I forgot to turn on my calculator. Okay, so 150 grams times 4.2 times 80. Okay, 50,400 joules. Is that a lot? It is a lot. That's why it takes forever. That's why I watch the pot never boils. Okay, or why it takes forever, because obviously it does boil. Unless you're watching it and the burner's not on. I've never done that before. Ever wonder why something doesn't cook and then you look down and go, oh, crap. All right, so for this one, 50,400 joules. Okay, that's a lot of energy. Water requires a lot of energy in order to change its temperature. All right, questions on the first one? It's pretty easy. All right, this one's going to require you to do just the slightest amount of algebra. Okay, so on this one here, okay, our givens are, we have the mass, 100 grams, okay, and we're looking for the material. Which part of the equation is going to tell me what material it is? C, yeah, specific heat capacity, because it's a physical property. All right, so I'm looking for C. I know the energy, 4,200 joules. Okay, and I'm looking to change the temperature by 50 degrees Celsius. All right, so E equals M times C times delta T, and I'm looking for C, so I simply divide both sides by M delta T. Okay, and so I'll have 4,200 joules divided by 100 times 50. 4,200, okay, divided by, and you have to do the bottom in brackets, 100, it was 100, right? No, 100 times 50, yeah. Okay, times 50, all right. So we are looking at a specific heat capacity of 0.84, so 0.84 joules per gram degree Celsius. So then I simply go to my chart, and, well, that makes sense, it's a cup. Should be made out of glass. That makes total sense. Okay, so that's the one we would go with. Okay, so our final answer here would be glass as the material. All right, questions on number 2? Okay. Try number 3. This is really as tricky as they get, okay, because there's one extra step at the end of this one. All right, let's have a look at this one. Because like I said, this one has kind of an extra step at the end that makes it just a little bit trickier, okay? Nothing that's going to tax you guys, but so we're looking for the final temperature. So we're looking for TF. Okay, we know the initial temperature is 7 degrees Celsius. Okay, it's heated with 200 joules worth of energy, okay, and has a mass of 185 grams and is made of iron. Whoop, sorry. I do know that, I just have to look it up. Okay, so iron, 0.130, right? No, 0.460, sorry.
Yeah,
0.460. See what I did there? Put the eraser in the black marker box. So I pick up the black marker. Thanks, I have the eraser. Smarter than me. Okay, 0.460 joules per gram degree Celsius. Okay, so if I want to find final temperature is not really part of the formula, but change in temperature is. So can I find change in temperature? Yes, I can. Okay, so I'm just going to go E equals m times c times delta t. Solve for delta t by dividing both sides by m times c. Okay, so I'll have 200 divided by 185 times 0.46. Okay, and so if I do that, that'll give me my change in temperature. So 200 divided by 185 times 0.46. All right, so I'm getting a temperature change of 2.35 degrees. Is that very much? No, but it sure makes the next calculation easy because it's a nice small number. All right, so that's going to give me my change in temperature. So it was 2.35, right? Yeah, 2.35 degrees Celsius. Okay, that's my change in temperature. Since I know my initial temperature is 7, my final temperature must be the change in temperature plus the initial temperature. Okay, which means 7 plus 2.35 is 9.35 degrees Celsius. Okay, so that's the extra little step at the end. Okay, so you have to either add if you're looking for final temperature or subtract if you're looking for initial temperature. Okay. Questions on that one? Pretty straightforward? Yep. Okay. All right. I would like you guys to try. You've got these in your digital workbook. So if you're looking down below the list of specific heat capacities, there's a heat capacity worksheet. Okay, it goes to like question 32. Okay, now I'm going to pick a few of these that I want you to do. Okay, I don't know if we'll get to them all or not, but I'm going to have you do a few at a time here. So what I would like you to start off with are question, let's say, question 1. So just write down these numbers. These are the ones I'm going to want you to do. Okay. 1, 6, let's say 12 and 16. That's a different sheet. Okay, let's go with those for now. 1, 2, 12, and 16 for now. Okay, 1, 2, 12, and 16. Let's start with that. I think I ended up combining these. They're the same questions, right? Yeah. Okay, so give those a try. I'll give you a little bit of time, and then we'll go through them together. Okay? So,
for question number 1, we've got Brianna stocking shelves and she notices smoke coming from another part of the store. When she reaches the back door, she finds the temperature of the door has risen 50 degrees Celsius. Not risen to 50 degrees, has risen by 50 degrees, kind of worded poorly. The temperature change is 50, okay, is basically what that is telling us. So the temperature change is 50 degrees Celsius. The door has a mass of 10,000 grams or 10 kilograms. Okay, and the fire has generated 230,000 joules worth of energy. Right? We're looking for what material the door is made out of. So when we manipulate, we're looking for C, so that'll be E over M times delta T, so that'll be 230,000 divided by 10,000 times 50. Right? And when we do that, we should get 0.460. Okay, which is our joules per gram degree Celsius, which is the specific heat capacity of fire. Okay. Everybody all right with that? All right, for number 6, okay, we have a 500 gram glass, so they're telling us the mass, 500 grams, and the specific heat capacity of the glass is 0.840 joules per gram degree Celsius. And the temperature of the glass drops by 15 degrees Celsius. Negative. Okay, this is going down. How much energy did the glass lose? All right, so that's an easy one. I don't have to manipulate. I just have to plug in my numbers. All right, so I'll have my 500 grams times 0.84 times negative 15 degrees, and I get negative 6,300 joules. The negative indicating the energy has been lost, given off, okay, in that way. Questions on that one? Okay. All right, so for number 12, photocopying some papers, the photocopier gives off 28 joules worth of energy, okay, to each mass of paper, or to each sheet of paper, which is 0.01 grams. Okay, the specific heat capacity of paper is 1.8 joules per gram degree Celsius. Okay, how much does the temperature of the paper increase after it is copied? What would happen to the paper?
Light on fire.
It would light on fire. Okay, this is a terrible question, because that is an unrealistic answer. Luckily, it's not an exam, where I would never put a question with an unrealistic answer. Okay, this would spontaneously ignite for sure. Okay, in this situation here. So we're looking for delta T. So E equals MC delta T, and we're just going to divide both sides by M times C. Okay, so delta T will be 28 joules divided by 0.01 times 1.8. Okay, and that's going to give us our 1555.6 degrees Celsius, which is redonkulous, okay, in terms of a realistic answer. Right? I mean, the paper comes out of the photocopier nice and warm, but you know, it's not going to turn your hands to goop because it's so hot. Okay, yeah, that's kind of a bit unrealistic. Okay, number 16. Kara is making itchy band. I haven't had itchy band for a while. I want itchy band. Okay, so she must heat water from 50 degrees to 100 degrees, and she's going to use 1 million joules worth of energy. Okay, I know that sounds like a lot, and it is. Okay, so what's the mass of water that she is heating? So we have the temperature change, 50 degrees Celsius. We have the energy, 1 million joules. Okay, and we are looking, and sorry, we know it's water, so we know this specific heat is 4.2 joules per gram degree Celsius, and we are looking for the mass of the water. So E equals M times C times delta T. Divide both sides by C times delta T, and we're getting M, so that will be 1 million divided by 50 times 4.2. All right, and we get 4,761 grams. That's almost 5 liters worth of water. That's a lot of Itchy Van, because Itchy Van only requires 2 cups of water for 1 package. Not because I've made lots and lots of it in my life, but it's 2 cups of water. Okay. Well, you're missing out. But get the chicken flavor, because the other ones are kind of gross, especially that shrimp one. Okay, so let's give you guys about a 5-minute break here, and then I'm going to have you do a few more of these, okay? I think I will have you do 3, 8. Okay, so take a 5-minute break and then I'll show you which other ones I want you to do. You can now try the ones I circled in blue. So that would be 3, 8, 14, and 18. So 3, 8, 14, and 18. These 4. So for number 3, okay, we've got this spoon that has gotten 5 degrees warmer. So our temperature change is 5 degrees Celsius. Okay, the spoon has a mass of 0.008 kilograms. How many grams is that? It's 8 grams. There's 1,000 grams in a kilogram. So 0.08 would be 80 grams. 0.8 would be 800 grams, so 0.008 is 8 grams. Yeah. Okay. So it's just we don't do metric conversions enough. So okay. So our mass here is 8 grams. Okay. So that's like a nice big heavy silver spoon. And we know that it has absorbed 50 joules worth of energy. Okay, we are looking for the specific heat capacity of the spoon. So E equals mc delta T, and we're looking for C, so we'll divide both sides by m delta T, okay, and go 50 divided by 8 times 5, right, which is going to give us 1.25 joules per gram degree Celsius. Okay, which means that stuff is, or that, well, it didn't ask us what it was, but there's nothing on here with a specific heat capacity of 1.25. It's definitely not metal if it's 1.25, so it must be like a plastic spoon of some kind. Yeah, it's 1.25. Yeah, so it must be plastic, but it's not. We don't have that number on here, so. All right, then we have number 8, okay, that we're looking at next. So someone is soldering 2 wires together, so they have to raise the temperature of the wire by 70 degrees, so they gave us delta T. Okay. The wires have a mass of 0.034 kilograms, that's 34 grams, okay, and they're made of copper, so copper has a specific heat capacity of 0.39. Joules per gram degree Celsius. Okay, and we are looking for how much energy is being given to the wires. So we don't have to manipulate, we just have to plug in for this one. E equals mc delta T, 34 grams times 0.39 joules per gram degree Celsius times 70 degrees Celsius. And that'll give us our 928.2 joules worth of energy. Okay. Questions on that one? And number 14. All right, so the space shuttle lifts off. 200 million joules worth of thermal energy are transferred to the launch pad. So, not a place to stand. Okay. The launch pad is made of concrete, and concrete has a specific heat of 2.9 joules per gram degree Celsius. And it has a mass of 500,000 kilograms, which is 500 million grams. Okay, because there's 1,000 grams in a kilogram, so we just put 3 more zeros on the end of it, and we've got it in grams. Okay, everybody with me there? All right, so that's the mass. So we are looking for the temperature increase of the launch pad. So E equals mc delta T, divide both sides by m times c, okay, and we're going to have our 200 million divided by our mass, which was 500 million, okay, times 2.9 joules per gram. Right? And when we do that, we're going to get that the temperature of the launch pad only changed by 0.13 degrees Celsius. Okay? Which, that makes sense. It's a lot of concrete. Concrete has a pretty high specific heat capacity. It's why we use it. I mean, not only is it strong, but it doesn't get hot, right, when the sun shines directly on it. So, not that you would walk around outside on the sidewalk with bare feet, but you wouldn't burn your bare feet if you did it. But, rocks and glass and stuff, so be careful. Okay, everybody with me there? All right. For number 18, if we're making French fries, okay, and deep frying them, we are going to heat vegetable oil, so we need the specific heat capacity of vegetable oil, 2. Okay, so we got that. So the specific heat capacity is 2.0 joules per gram degree Celsius. It's heated from 20 to 85, so our temperature change is 65 degrees Celsius, and takes 50,000 joules worth of energy. Okay, we're looking for how much oil is in there. Okay, so E equals m times c times delta T, and we're manipulating for mass, so divide both sides by c delta T. Okay, and we will have 50,000 divided by 2 times our 65. Okay, and that means we will have 384.6 grams of vegetable oil. Okay. All right, how are we feeling about these? Okay with these? Okay, because doing these is, there's going to be a 5-mark question just like these ones on your unit exam. One for givens, one for picking the right formula, one for manipulating the formula, one for plugging the numbers into the formula, one for getting the right answer.
I like the right formula meaning
Yes, E equals mc delta T. I have to be consistent. In every other unit I've given you a mark for picking the correct formula, even in chemistry where you had one formula. N equals little m over big N.
We'll take it.
I would, stop arguing with me. Don't try to talk me out of it. Yeah. Okay, we definitely want to give you marks for your method, right? So that's what I'm doing there. This is also going to be part of the other thing we're going to look at starting tomorrow, and that's latent heat. Okay, in latent heat, we use this as part of the heating curve of water. So we have to be able to calculate how much energy is involved in warming or changing the temperature of either ice or water or steam. Because I don't know if you noticed this on your chart here, but because water is weird, it actually has a different heat capacity in different states. Not all things have that. Okay, but water, when it is a liquid, is 4.2. When it's a gas, is 2.2, and when it's ice, it's 2.116. It's in there somewhere. There's ice, 2.116. Okay, and steam is at the bottom. Yeah, 2.02. Okay, so yeah, they all have a different heat capacity. Oh, don't pack up. Don't pack up. Okay, I'm going to pick 3 at random. And you guys are going to do them, and then we'll end off that way. So, let's go 3 and 7 and there's a change in temperature one. 3, 7, and 10. Okay, I want you to try 3, 7, and 10 here.